All right, good. Thank you for dressing up. I was looking for someone. That continues our legacy. Here we go. Thank you. Welcome to class on the Halloween morning. Not the time for party yet. We still have a bit of things to do today. So I want to start by talking about this example. So where are we? We were talking about conditional distribution, two random variables, a pair of random variables x and y, and we want to look at the conditional expectation, expectation of x given y. If you were not here for the past couple lectures, let me remind you what we have been doing. We've been talking about this thing, px, which is the probability density function for the single variable. And then we were talking about this conditional density function, p of x given y. Now, the relationship between the two is that p of x given y is just a p of x and y divided by p of y. That's the definition of the conditional density function. It is a smaller quote-unquote sample space, a subset in the sample space that you want to pay your attention on. So this is the definition. Now, anything that you have done in the one-dimensional PDF or PMF can be done also on the conditional density. For example, if you calculate the probability of a random variable x inside the set A, then you can talk about the probability of x inside the set A given that the random variable y equals to the state of y. So what you have added is this condition, that y is on a certain event. We can also talk about the expected value. So the expected value of a random variable x is, of course, just the integration of x and then px, integrate over x. And here, you can talk about the conditional expectation of x, given that y equals to small y, and that is defined as the integral of x, p of x given y, dx. So you can see whatever you have done in the one variable case, you can do it the same for the conditional density function. There is a relationship between these two, which is that if you want to look at the expected value of x given y, now this is a function of y. It's a function of y. If I multiply it with f of y, here I'm using py, and if you integrate this thing over all the possible y's, then you will get back the expected value of x. So this is nothing crazy. It's just that I have a set. I have a sample space, a partitioning into the different pieces, and then I have an event, which is the, let's say I want to calculate the expected value. I have an event A here. I just divide it into smaller pieces. Each piece is a conditional expectation or conditional probability, and then I need to weight it using the weights for each segment, y1 and 2 and 3. Then I integrate them, then we'll get back the original thing that I want to look at. So there's a decomposition rule. All right, so the formula is a bit difficult, but then when you look at the example, it will be more obvious. So here's the first example. Suppose that two classes of cars, x be the speed of, x will be the speed and c is the class. In this example, I assume that if class c is 1, then we know that the random variable x will be a Gaussian with a certain mean mu1, a variance sigma 1. We know that the probability of class being class 1 is p. Now, if you're class 2, you have another Gaussian. The probability of getting the other class will be 1 minus p. So you can imagine that there is a van that is, what car is this? Is it a Ferrari? I don't really know. Okay, it's a good thing that you don't know. Okay, it's like when you can taste the difference between different wines, then you become picky. So for people like me, I don't really know. So even if you fool me, I'll be pretty happy. So that's a good thing that you don't know. All right, so never mind. So we have two different types of cars. They have two different Gaussian distributions, mu1 and mu2, sigma1 and sigma2, and you are in different class, right? Okay, so the question is that suppose you see a car, you see the car on the freeway. What is its average speed? What is its average speed? So this question requires you to do the decomposition, because if you pick the first car, then you have a lower mean. If you pick the second car, you have a higher mean. So I do just tell you that, hey, you see a car on the freeway. You don't know which car it is. I ask you, what is on average, what is the speed? So you can do this decomposition. You can find out the expectation. All right, so how should we do it? Well, let's look at the first class, class 1. Okay, class 1. Suppose you're class 1. Suppose C equals to 1. Then what would be the distribution? Well, the distribution is Gaussian. So it means that you have 2 pi sigma 1 square e minus x minus mu 1 square divided by 2 sigma 1 square. This is your Gaussian distribution. But what is it? Is it f of x? Is it f of x? Now, x is the speed of any car. I give you this formula, Gaussian, for the first class. Is this fx? Or is it x given class 1? Which one? X or x given class 1? You have two choices. This or this. Which one? Is a generic distribution for the speed x, or is a constrained set where x is constrained on class 1? Constrained. Okay, I hear that, constraint. So it is this x given class 1. That's the conditional distribution. So now, of course, you can say I want to look at class 2, then you have another formula, 2 pi sigma 2 square e minus x minus mu 2 square divided by 2 sigma 2 square. Okay, so you have two classes. So class 1 and class 2. C equals to 1, C equals to 2. Now, I also have two probabilities, P and 1 minus P. What are they? Well, they're just F C1. This is P. F of C2, it is 1 minus P. So these are given to you by the problem. Then what do I need to find? Well, I want to find the average speed. Average speed. So I need to find expected value of x. Now, what is the expected value of x? Well, expected value of x is integration of x, and then you have fx dx. Integrate over the entire sample space, omega. Oh, no, I don't have access to fx. No, right? This is fc and then fx given c. What should I do here? Any suggestions? Yes, please. Okay, great. You can graduate. Okay, so you got the principle. So the first one is the idea is that you have the decomposition, of the two conditional probabilities, and so what you can do is that you can look at this x expected value of x given that you are at class C1, and then you have expected value of x given that you are class C2. Okay, your two expected values. Now, these two expected values, they're conditional expectations, given on C1, given on C2, decomposition, right, into two halves. And then what is the probability of getting this? Well, it is P. The probability of getting this is 1 minus P. Okay, because they're weighted. If you have more chance of getting this car, then, of course, this mean will matter more to your overall probability, expectation. Okay, so now when you go to this formula, then the rest is calculus. What is the expected value of x given C1? Well, the expected value of x given C1 is the integration of x times your fx given c1 dx, right? So it's this thing here. The other one will, of course, be replace the c1 by c2. But let's ask, what is this? Well, you say, okay, I have a formula. This is integral of x times 1 over root 2 pi sigma 1 squared e minus x minus mu 1 squared divided by 2 sigma 1 squared dx. Whoa, very complicated formula. Then I need to start to do this integration, and then integration by part, and then substitution, and Of course, that will make you cry. And I can tell you, you don't have to do that. I can tell you the answer immediately. What is the answer for this integral? Not 1, yeah? Mu1, okay, mu1. Why? Because this is Gaussian. It's a Gaussian distribution centered at mu1, and you are just calculating the expected value of that specific Gaussian, okay? So this will give you mu1. Okay, so what does it mean? Well, you have this sum of two expectations. This is mu1 times p. The other one is mu2 times 1 minus p. Okay, very intuitive. You have two different types of cars. One is a mu1, one is a mu2. The chance of getting car 1 is p. The chance of getting car 2 is 1 minus p. Of course, the average will be p times mu1 and 1 minus p times mu2. Add them together. So that would be the average. Okay, so you see that the conditional expectation for this problem is actually one step. Okay, the formula, if you go back to the very beginning, you look at this formula, holy cow, this is so complicated, right? You have this conditional distribution and then x and then so on and so forth. And then you look at this decomposition rule. It's so complicated on this formula, just generic formula. But once you sit down and do the thing, it's that simple. Okay, so don't overthink that it is very, very difficult concept. It's just decomposition of the random variable into two different pieces. Let's work on one more example so that we will become more familiar with this idea. So we have filled up this slide. Okay, so example 2. Example 2 is this. You have a joint PMF given by this table. And I want to find the conditional expectations for these two cases. Then, of course, I can also ask you, let's find the expected value of x. OK, so let's take a look at this table. This table has 2 rows and 5 columns. It is the joint distribution. So this is p of x and y. Not x given y, not y given x, but it's x and y. Now, if I want to find out the expected value of x, what I should do is different approaches, right? The first approach is the lazy approach. You just take the marginal distribution by summing the columns, then you get px, then you do the usual thing to get the expected value of x. Right? So that's the marginal approach. But I want to demonstrate in this example, how do we use the expectation to do the calculation? So how should we do it? Well, it's a longer path, but it's really for the purpose of education. Okay, if you are given this problem, just calculate the marginal, you can get the result. Okay, so how do we calculate these two expectations? Well, these two expectations can be found by finding the conditional distributions and then take the summation. And once you have these two, to get this expectation, just do what do we call the law of total probability, right? So you decompose it into 2 halves, and then each one has a different probability. Okay, so let's look at this. Expected value of x given y equals to 10 to the 2. Okay, so this is the conditional expectation. To find this, I need to do x times p of x given 10 to the 2. Right, so this is the conditional expectation. And this is discrete, so I need to sum over all the possible x. So by looking at this table, clearly I don't have access to this conditional probabilities yet. Okay, so I need to find out. Now, how do I find p of x given 10 to the power 2? That's not too bad. that is just P of x and 10 to the power 2 divided by 10 to the power 2. Okay, so that's just the definition of conditional probability. And what is this? This is 5 over 12, 5 over 18, and then 5 over 36, 0 and 0. So these are the 5 numbers for the second row. Divide by the marginal. The marginal will just be the sum of these 3 numbers, right? So you have 5 over 12 plus 5 over 18 plus 5 over 36. So you will get 3 numbers. So let me see what are 3 numbers. So you get 1/2, 1/3, and 1/6. So you have 1/2, 1/3, and 1/6, 0 and 0. Okay, so this is your conditional density, conditional mass function for this table. So starting from this table, you do this calculation, just the definition, you can find this conditional density. And once you have this conditional density, you go back to here. So here you have the summation of x times the conditional probabilities. So how should we do it? Well, you look at this table. You have 0.01 will go with this probability. So you have 0.01 will go with 1/2 plus 0.1 will go with 1/3, and then plus 1 that will go with 1/6, and you have 0. Okay, so you do the calculation, and let me look at the answer. This is 123 over 600. I'm not going to ask you to do this tedious thing in the exam. Okay, but okay, this is a number. This is a number. So you have found the conditional expectation of x given y equals to 10 to the power 2. So that is the second row of your table. Then you can do the same for 10 to the power 4. And once you find that, you will have expected value of x given y equals to 10 to the power 4. Just do the same thing. And if you do it right, you will get, what is the value here? 123 over 6. So 123 over 6. Then I want to find the expected value of x. The expected value of x will be expected value of x given y equals to 10 to the 2 plus the expected value of x given y equals to 10 to the power 4. So that is a probability of getting that. So we also need to find out what is the probability of getting that. Do I have the number here? I don't have the number here. So I need to find out the probability. So this is the probability of y equals to 10 to the 2. This is the probability of y equals to 10 to the power 4. You guys need to help me how to calculate this. So 12 over 5 plus 5 over 18 plus 36 over 5. So this is 36. Holy, this is what? 30? Okay, I trust you. Okay. Okay, so you take the responsibility. Okay, so this is some number times, this is 30 over 36 plus the other number times 6 over 36. Okay, so assuming that we are right, then we will be able to get to the final result, which is 3.5875. 3. What? Okay, 5875. Again, I promise I won't ask you this in the exam. This is just too tedious for me, and so I don't want to pass my unhappiness to you. So you won't be asked to do this kind of tedious calculation. But anyway, I think you see the point, right? So find the conditional expectation, find the probability, marginal, you got this result. Again, for this problem, you don't have to do it in this way. If the final purpose is to find the expected value of x, just do the marginal, you can get a result. This is a demonstration of the concept that we have been learning. Okay, good. So let's move on to one more example. This is a little bit more complicated example, and if you can understand that, you'll be good. So this example says that you have two random variables, x and y. X is a Gaussian distributed according to this distribution, mu and sigma square. The other random variable y is a conditional distribution, y given x. Y given x, and that is Gaussian of x and x squared. Well, this is very ugly. Okay, why? Well, okay, so let's look at the first random variable. That's easy, right? So it's a Gaussian. The second random variable, y, is a random variable depending on x. What do I mean? So the first random variable is a Gaussian. Gaussian with certain mean, let's say 0 mean, and then there's a unit variance. That's your x. This is your fx. And you have a bag. You put your hand into the bag. You pull a number out. That number will have a distribution according to this shape. So you have a more chance of getting the mean. You have a lower chance of getting a bigger number, a small number. So let's say today you do this experiment, you get this number. This is 0.72. Okay, this is a number you pick. Then what would be the distribution of y? The distribution of y, okay, y will be a Gaussian that has a mean of 0.72 and a variance of 0.72 square. So what I mean is that you have a Gaussian centered at 0.72, and then the variance is 0.72. If tomorrow morning you wake up, you do another experiment, and you pick a number to be here, 1, okay, to be 1, then let's say this is 1. Then your distribution of y will be centered at 1, and then the variance will become 1. So this is your distribution of y. You get a different distribution. Okay, so that's the problem. And so now I want to ask, find the expected value of y. Now this is y given x. Okay, so I condition on x. I want to find the expected value of y. Right. So how should we do it? Any suggestions? The same principle. Anything? Decomposition. Right. How should we do it? Now, the difference between this problem and the previous two problems is that in the previous two problems, there are only two classes for y. P and 1 minus p. Okay, and some number versus the other number. Here you will have a continuous distribution for these numbers, these cases, these classes. You just have a continuous mapping for these classes. Yes? Okay, so that's one suggestion. Let's try that. How about that? Okay, so so the suggestion is that I have fx, I have fy given x. That means I have x and y, which is the fy given x times fx. Correct? Okay, and then I need to do the fy. This is going to be the integral of fx y dx. And once I find this fy, then I can find the expected value of y. That will equal to y times fy dy. Right? I think that's the logic here. Okay, so let's see why this is not a good idea. Okay, I will convince you why this is not a good idea. So let's first do this. It's doable. It's completely feasible. But it's just not fun. So let's do this. This is integral. And here this is your y given x. This is 1 over 2 pi what? The variance. The variance is actually x. And then e to the power minus y minus x squared divided by 2x squared. This is your fy given x. Why? Because the problem tells you that this is a Gaussian of x and x squared. And so your distribution, your conditional distribution, your fy y given x is this. This is your fy given x. Not too ugly yet. Okay, so now let's multiply something. It's called the distribution of x. So you have 2 pi sigma square e minus x square, x minus mu square divided by 2 sigma square. And then what do you need? Dx from minus infinity to infinity. Okay. It's not too hard, right? Just that I don't know how to solve it. You have x in the denominator, and then you have x in the numerator, and then in the exponential. So that's not fun. Okay. Any comment on that? Oh, this is not yet, because we're trying to find f of xy. This is the joint. Okay, great. Okay, so I convinced you that this is not a good path to go for. Okay, so what is your second option here? Okay, you will be the second one to graduate. Okay, all right, great. So, so how should we really tackle this problem? Well, this problem has this f of y given x, right? Y given x, y given x. That means I can find expected value of y given x equals to a state of x. I can find it, right? Because I have y given x, so I can find this expected value. If I can find this expected value, then what would be the expected value of y? Expected value of y would just be the integral of this expected conditional expectation, x given x. And what should I have here? It will just be f of x. dy or dx? Very confusing. dy or dx? X, oh, I'm sorry, you need to take a course again. This is not x. It should be y. It should be y, okay? Oh, it should be x. Okay, I need to retake the course. Okay, it should be x. Sorry about that. Okay, you're the third one to graduate. Okay, integrate this. All right. So the reason is that it is x because your y, the randomness in y has been taken care of already. Right. So there's no randomness in y anyway. This is going to be a distribution over the x because this is the distribution for x. Okay, so how do we do it? Well, this thing I know. This is just a Gaussian. 2 pi sigma square e minus x minus mu sigma square divided by this. This is your Gaussian. How about this number? This number is the conditional expectation of a Gaussian. All right, so let's write down the formula. It is x, this is y times 1 over 2 pi x squared e minus y minus x squared 2x squared dy. Okay, that's the definition of this conditional expectation. Now, if you get confused about all the x and y's here, let me tell you the way I teach my daughters. When you see something you don't like, just replace them by an apple. Then you will be very clear what you're doing. Okay, so replace this by apple. Replace this by apple. It's by apple. You only have y left. So you have to integrate with respect to y. That's the point. Okay? So you integrate with respect to y, and what is the integration? The integration of this y times something Gaussian with a mean of an apple, variance of apple. That's just the mean of a Gaussian. So the answer is that it is just the apple. And what is the apple? Apple in this case is x. Follow the logic here? Okay, so you have y and x, a lot of complicated things. But since you're integrating with respect to y, anything you see the x, replace it by the apple, orange, banana, whatever you like, then you're just integrating the Gaussian. And you're finding the mean will just be that thing. In this case, it will be x. And since this is x, and what would be the thing here? This is just the integration of x times the Gaussian. So the expected value of y will be the integration of x times your Gaussian, 2 pi sigma square e minus x minus mu square divided by 2 sigma square dx over the entire sample space. And this is mu. Okay, problem solved. All right, so this problem looks a bit complicated, a little bit tedious. If you look at this drawing here, oh wow, my variance is changing, my mean is changing, everything is changing. But ultimately, when you sit down and use this decomposition rule, it's actually just a couple steps. Really, I don't even need to write too much. It's a couple steps I can get to this conclusion that the mean is of y is just x. Okay, it's just mu. I hope these three examples are giving you the idea of whenever you see conditional expectation, number one, do not freak out. It's just a smaller sample space that you are looking at. And the key tool that you will be using is this decomposition rule. You look at the individual conditional expectations, and then you look at the probability of getting these individual expectations, then you sum them up or integrate them. That will give you the final expectation. All right, so I hope this sort of clarifies a lot of misconceptions. It took me a while to understand it when I was a student, but once I understand it, I explain to you again. I hope that you don't have to go through the same torture in understanding this concept. Is it good? All right, good. Questions? Let me pause for a few seconds in case there are questions. No questions? Good. All right. Okay. Sum of two random variables. Again, it appears, how should I say it? It can be as tedious as you can imagine, but the principle is very simple. The principle is very simple. Let me start by telling you examples. Okay, let me start by telling you examples. And then we can go back to the principle. Because otherwise, it's very difficult to get any concrete understanding. Let's start with this. Okay, let's start with the examples. So what is the deal here? The deal is this problem. So don't worry, I will go back to 5.6. Okay, once we see the example. The deal is this. You have two random variables, okay, x and y. The PDFs are given. And I want to find the sum, x plus y, define it as z. I want to find the PDF of z. I want to find the PDF of z. So in this case, you have two distributions. I don't know what they got called, but there were two distributions. I want to find the PDF of z. Now, before I work on this example, let me just give you an easy example. Do you guys still remember the throwing a die example? You throw a die, you get number 1, 2, 3, 4, 5, 6. You throw the die twice, what do you get? You get 2, 3, 4, 5, all the way to 12. How does the PMF look like? You start with a uniform. If you have two dice, triangle, right? Remember that? You get triangle. Where does this triangle come from? You never add the two PDFs. If you add the two uniform PDFs, it will just become a taller PDF. It's not adding. But it's about doing this convolution, right? Two PDFs, shifting left and right, and then now the two rectangles, when they are completely overlap, you get the maximum, and then they slide away, then you get a lower value, right? So this is the convolution. So people are already shaking their heads. Okay, so that's going to be the nightmare, okay? But the same principle here. When you have two random variables, when you try to add them up, you're doing some sort of convolution like that, okay? So that is the principle. So why is this the case? Let's just look at this example, and we will understand it. Oh, by the way, why do we want to do this? Why do we want to sum two random variables? Summing two random variables is usually not what we do. Usually we're summing 100 or 1,000 random variables. Why? Because you never take measurement once. You always take measurement multiple times, and then you take the average, and then you want to calculate its statistics. The moment you start to take average of multiple random variables, you are summing them up. And so the convolution is there as soon as you start to talk about the sample average. So this is unavoidable. And I will show you that when you have a lot of random variables together, and as you're summing them up, the distribution, no matter what you start with an exponential, you start with a binomial, you start with whatever, and as long as you start to sum them up, it will converge to a Gaussian. Oh, very powerful result. Okay, so I'll show you that. And so in order to explain that thing, I need to talk about how do we sum two random variables and then multiple random variables. So how do we tackle this problem? Well, of course, you don't know how to tackle this problem. So let me tell you how to tackle this problem. There are a few steps to tackle this problem. Let's do this reverse engineer approach. What do you want? At the end of the day, you want fz, right? You want a PDF of z. So let me write fz here. So let's go backward. If you want to find fz, what do you need? Well, to find fz, the only thing I have learned so far is that it is ddz of fz. Okay. So this is the fundamental theorem calculus. You take the derivative of your CDF, you will be able to get the PDF. Okay, good. Now, reverse engineer, how do you get fz of z? Fz, how do you get it? Well, by definition, this is just the probability of z less than small z, right? So that is the probability. Now, how do we get this probability? So probability of z less than small z, this is the probability of x plus y less than small z. By the problem, because I'm defining big Z as x plus y. Okay, so a couple of steps, right? If I can solve this problem, I will be able to solve this one. If I have this one, I can do this, and then I can do that. Okay, reverse engineer process. Does it make sense to you? Very logical. Okay, so let's start with the beginning. How do we find this x plus y less than or equals to z? So let's start with this. Probability of z less than small z, which is your CDF. So this is the probability of x plus y less than or equals to z. And so for this problem, I need to calculate this probability, right? X plus y. So let's draw the diagram here. There is an x-axis, there is a y-axis. There is an xy axis and there's a y-axis. Clearly, if I want to calculate this probability, it will be fx and fy. Now, it's a product because they're independent. Technically, I need to start with a joint distribution x and y, but since they're independent, I can just write them as a product of these two. I need to do this double integration, dx and dy, over the set, over the event that I'm considering. the event that I'm considering is x plus y less than or equals to z. And so I should start with a 2D plot, and the equation would be y equals to minus x plus z, right? Because this is x plus y equals to z is equivalent to y equals to minus x plus z. So what should be the line that is defining this? Or of course, it has to be diagonal. Is it the positive slope or the negative slope? Positive or negative slope? This or that? A or B? B. Excellent. Okay, so that's B. Okay, so the next thing, is it on this side or is it on that side? Okay, so principle. I make z to be positive, right? Z to be positive, so z is up here. Put the number 0, 0. Okay, 0, 0. The 0, 0 is here. And it should be what? Well, y, this is less than, right? So it has to be like this. So 0, 0 has to be less than z. So it has to be included. And so it should be this side. This side. Okay. And what else? Well, my x has to start with 0. So it has to be just this triangle. Not from minus infinity to infinity, but from 0 to infinity. Okay, so that would be a triangle. But anyway, so let's before we go into this specific problem, in general, when you have this problem, when you have a problem like this, right? When you have a problem like this, you can start with minus infinity to infinity, and you need to put the bounds for the x and y until you see the particular example. In general, when I just tell you, hey, you have x and you have y, in general case, you start with minus infinity. Okay, right. Anyway, so let's talk about this integration. This integration, for this example, it will be what? Well, you integrate with respect to x first. If you want to integrate with respect to x, what would be the lower limit for this example? 0 to where? Where do you stop? This point. Yes. Z minus y. Okay, z minus y. Excellent. Okay, and then y has to go from 0 to z. Okay, the upper limit is z because this point is your z. And z is the arbitrary number I pick for now, and they can become bigger numbers, right, later on. Right? So it will be this double integration from 0 to z minus y, 0 to z. That will be the integration, double integration. Okay. So now you put in this, and then you start to cry because it's a very tedious double integral. The good news is that I never asked you to calculate this precisely. I just asked you to find this. And you can put the derivative right now. You can put the derivative right there, right? So, so what do we want? Well, let's do the derivative. Let me see. How should we do this derivative easier? Let me see if I have. If I have a slide. Okay. So this one. Okay. So for this one, it might be easier to. I just look at this result here. It might be easier to. What am I doing here? Well, I'm going to ignore it. So let's just do it. So what is your fx? This is the double integration from 0 to z minus y, 0 to z, of your fx. Fx is xe minus x, and y is e minus y, dx and dy. Okay, dx and dy. So if I want to integrate this thing, if I want to integrate this thing, then I have a z here. What should I do? Let's just integrate the inside. Okay, let's just integrate the inside. So if you integrate the inside, then you have this 0 to z, and then your y will come out, dy, and of course, dy will be outside. And now you have to do this integration, 0 to z minus y, xe minus x dx. Okay, so how should we do this integral? Well, this integral is it by part? I think it's by part, right? So you have xe minus x, and then that will be a z minus y, and is it 0? And then minus e minus x, and then you take the integration from 0 to z minus y, and that's dx. I hope I'm right. Okay. Then you do this calculation. Well, maybe I'm doing something wrong. I don't want to mess up. How about this? How about we do it next time? Because I'm afraid that I'm making some stupid mistakes here and there because I'm really bad in calculus. So let's do it next time. When I have sit down and then do it once on my paper, I don't want to tell you the wrong story. But the bottom line here is this. Okay, I still have 2 minutes, so I can explore that. The bottom line is this: you want to go through these steps. You want to go through these steps. You want to find out this probability, and then you want to take this derivative, and then from the derivative, you want to get the final result. Okay. So we're done with this part. I think we are halfway done with this part, and finally, we just need to complete this part, and then things will be done. Okay. I just need to sit down and be very careful of all these symbols here and there. Make sure that my calculus memories come back. This integration by part is here. Then we'll be able to solve it. Okay? So rather than wasting your time and then seeing me doing all the crap, we'll just dismiss earlier, and then we will continue the story next time.